podcast is brought to you by LMU Munich.
Is a wedge of SNs. So what homotopy type means is if I ignore the fact that it was attached on the boundary, I could smoothly contract it onto a lower dimensional guy. That lower dimensional guy would be a bunch of n spheres, one spheres in my case, which would all be joined together at a single point. So that's a typical picture of a wedge of spheres. So this picture of Milnor's gives us a complete understanding of the topology of the guy that's nearby. And there's one additional piece of information which is really useful to know about the singularity, which is there's a monodromy map. If you take theta goes to theta plus 2 pi, if you go once around the circle, then you act on the nth homology of the Milnor fiber by somehow doing something to the classes of these spheres. So it permutes with coefficients somehow the SNs. Okay, so yes. Yes, thank you. So this is the basic topological information when we do a deformation of a singularity. We get a nearby smooth guy. We have some middle dimensional cycles which are going to zero size when we get down to the singular guy. That's what these n spheres are. And moreover, those middle dimensional cycles have some interesting monodromy action which helps us understand what's happening as we approach the singular point. So, the only information that I got out of the resolution in this complex codimension 1 case was that deficit angle. But I get more information out of deformations because when I look nearby, I see all of this structure. I see all these so-called vanishing cycles, that's what these SNs are, together with a monodromy action on vanishing cycles. Okay, so for this one, I'll give a much simpler example. Actually, I'll give two examples. So the first example is the simplest one-dimensional singularity, which is just a non-degenerate quadratic singularity. Yeah.
I think if you use this, you should also use this one at the same time.
Okay.
Otherwise it gets worse and worse, and
okay.
at some point you cannot read it.
Okay. I don't know how to use this technology, so. Oh, okay. So this is a better choice.
Just maybe not now anymore.
Okay.
It's too wet already. But yeah, if you prefer to not use water, then of course you can use a sponge.
Okay. Thank you. Okay. So here I have a simple example, which is f of xy equals x squared minus y squared. Yes? Absolutely. Thank you very much. I forgot what my n was. It was Cn plus 1, actually. Yeah. That's his point, yes. It's supposed to be plus. But this Sn is correct. So the simple example is this quadratic singularity in C2. And the picture here is, I have some kind of cone describing the singularity. So this is a really classical picture. And then nearby, when I do the deformation, I have a nice hyperbola. So this is x sub t, can you see the blue? Maybe not. Yeah? Okay. This is x sub t, and this is x sub 0. So that's what the picture looks like of the deformation. The Milnor story has this thing sitting inside of a 3-sphere, so it's a little...
Can I erase this?
Yeah, sure. So it's a little tricky to see it inside of a 3-sphere, but inside of a 3-sphere, I've got the two circles which correspond to x equal y and x equal minus y, intersected with the 3-sphere. And then this central guy is singular, but the nearby guys are, as advertised, homotopic to a particular circle. There's, in this case, a wedge of just one circle. So you don't really have to wedge them since there's one circle in the Milnor fiber. So this is a picture of the Milnor fiber with its, the Milnor fiber is in white, and gamma, which is the boundary of the Milnor fiber, is in purple, sitting on the sphere. So in this particular case, we can also say something about the monodromy. And the monodromy goes like this. So at one point of the circle, I've got, so here's my parameter circle S1. Here's my e to the I theta point. I travel around this circle, and I rotate the waist that attaches the two halves of the hyperboloid as I do it according to theta. So rotate the attaching waist with theta. So what I mean is that I'm going to take this top half and glue it to the bottom half with an offset, and my offset is going to be by theta. So I start out with no offset, but then as I wander around, I make this twist right at the waist. And when I've come all the way around, I've made a complete twist of the entire thing. And I end up with a monodromy transformation on all of the first homology of the fiber, which takes a class 2, the class plus its intersection with the S1 times the S1. So that's just a fancy way of saying what happens what happens to other classes on this surface when I do the twist. So that should really be relative to the boundary. It's the monodromy relative to the boundary. And a class like this one, which is a homology class relative to the boundary, or cohomology class relative to the boundary, gets some effect where you have to add in one loop around because of the additional twisting which happened as you went around the circle. Okay, so implementing this Milnor picture, figuring out the monodromy is generally pretty complicated. But what I want to do in my remaining 20 minutes is set up a situation in which we can actually make use of these monodromies. It's also a situation which is related closely to, anyway, it's related to some other things I said, and I'm somehow going to get to the end of my lecture within 20 minutes. Let's just say that.
Well, how can we recover the original singular picture from this
So it's difficult to see exactly what the structure is nearby. The main clue we get is that this waist shrunk down to 0 size. So seeing that it's, so in this particular case, it's a metric cone, but in general, it's difficult to understand, particularly in higher dimension, it's difficult to understand exactly what kind of structure you're going to get nearby. However, I mean, right at the singular point. However, you get information about how the non-singular variety is changing as you approach the singular point by studying this monodromy action. So, so maybe there's a second simple example. Well, I think I'm going to skip my second simple example. let me give a global setting to this story. So the global setting is going to be the construction of F theory, which is related to what we've just been doing in several interesting ways. So James already mentioned F theory briefly. F theory is a way of compactifying the type 2B string theory utilizing the SL2Z symmetry of the string theory. So the type 2B string has an SL2Z symmetry, and moreover, there are D7 brane solutions in this theory, which act as a source for the Ramon-Ramon scalar. So James mentioned this interesting quantity, which one forms out of the Ramon-Ramon scalar plus the dilaton. So there are two scalars in the type 2B theory. You can make this complex combination. And the D7 brane solution has the property, well, the D brane solutions generally have the property that they source the corresponding Ramon-Ramon fields. This is the brane associated to the Ramon-Ramon scalar. And what that means is, let's see, a D7 brane is 7 plus 1 dimensional, right? That's where the singularity is. So there's a transverse space which is 2-dimensional. And the brane is located at points in that 2-dimensional space. So the fact that it acts as a source means if you go around this point in the 2-dimensional space, this is real 2-dimensional, so one complex dimensional. It's the same sort of thing I've just been doing. If you go around the source, around the point, you end up sourcing the field. So tau goes to tau plus 1. You increase, if you normalize the units correctly, you increase tau exactly by 1 unit by going around. If you were to put a stack of D7 branes, so if you were to put n D7 branes, then tau should go to tau plus n. And that's a case where the general constructions of brane solutions suggest that there should be an SUN gauge symmetry in the story associated to that collection of branes on top of each other. So the usual picture for why that SUN gauge symmetry emerges is that there are open strings which connect the branes that are sitting on top of each other. If the branes were almost on top of each other, those open strings would transform according to a matrix in UN. There's a center of mass degree of freedom which reduces the gauge symmetry to SUN, and the mass of the brane would be, the mass of the string would be proportional to the separation distance, so when we bring them together, we actually get massless SUN gauge symmetry. So, sponge. So F theory is a way of exploiting these properties of the 2B theory to build string compactifications. So the F theory compactification, what I want to do is find a multi-valued function tau with an SL2Z symmetry. So it should be a function of a complex parameter. So Z is going to live in my 2-dimensional space here. It's a function of a complex parameter, and it has tau goes to tau plus n behavior near certain points. Well, there's one more fact about the D7 branes that I want to mention, which is that the D7 brane metric, instead of pushing the point to infinite distance, it has a deficit angle. And this just follows, it's hard to get a brane solution to work in a particular dimension. Together with the corresponding p-form field, there's some real constraints on the thing. I'm not going to write out the whole solution, but it has a deficit angle of precisely 2 pi over 12 for a single D brane. And I guess I would get 2 pi n over 12 for n branes stacked together. So the picture from algebraic geometry that I want is some kind of one-dimensional algebraic variety. So this should be some complex curve. I should have some points, P1 up through Pk, and maybe some brane multiplicities, N1 up through Nk. And I should have tau goes to tau plus Ni near certain points P sub I, something like that. Of course, it's multi-valued, and so if I do the tau goes to tau plus Ni, the coordinate in which it's goes to tau plus Ni might actually be a little different at these different points. So I kind of have to take that into account as well. And there turns out to be a nice solution, or a class of solutions to this, that comes from algebraic geometry. And these solutions lead to what's called the F-theory construction. So to explain these, let's see. The other feature here, right, is that because this is the exponentiated dilaton, the imaginary part of tau is definitely positive. And one of the classical pieces of theory is if I take the upper half plane, which is the set of tau whose imaginary part is positive, and I mod out by SL2Z, I end up getting what's called the J line. It's a copy of C. If I look in the m tau goes to infinity limit, and I sort of add that point, then C kind of gets included in a P1. So there's a way of compactifying that J line in a natural way. That story doesn't have anything to do with algebraic geometry. The place where it has something to do with algebraic geometry is the natural emergence of SL2Z as the symmetries for labeling a lattice whose basis is 1 in tau. So if I form a lattice whose basis is 1 in tau and act on it by SL2Z, then I get another lattice which is completely equivalent. This is known as the elliptic curve. It's a torus with a complex structure, two torus with a complex structure, labeled by that tau, and it's invariant under SL2Z. If you act by SL2Z, you get a completely equivalent curve. So, yes? I'm sorry? Yes, thanks. Okay, well, that one I think, because it didn't get washed, is dead to me. So there's some beautiful 19th century mathematics done by Weierstrass, which helps understand the behavior of these SL2Z invariant functions. So given an elliptic curve like that, Weierstrass sorry, I didn't print this one out. I'm trying to look at the notes from the laptop, which is being really slow. So my Z, let's pretend that letter wasn't Z. Actually, maybe I'll just change the letter here. So it'll be W, 1 over W squared, plus the sum over Mn not equal to 0, 0, 1 over Z plus M, that's a W, W plus M plus N tau squared, minus 1 over M plus N tau squared. That turns out to be a doubly periodic function on C with periods 1 and tau. And this is how, you start with this desire to have an SL2Z invariance. You realize that you can get that SL2Z invariance by complex torus, and now you turn it into algebraic geometry by this clever introduction of this function. So this has a double pole at each lattice point. You're really required to do something like that. If you were looking for a doubly periodic holomorphic function, it would have to be constant, but a meromorphic function we can do something about. And then there's this very cute trick. You take the derivative, which you can do term by term. I won't write it out. That derivative involves, well, I will write out that it involves minus 2 over W cubed. So it's not unreasonable that you could get rid of the polar terms by employing expressions like rho prime squared and rho of W cubed, and maybe some other things, some nice expression, which in the end of the day would give you some equation satisfied by the quotient C mod the lattice 1 and tau. So that's what Weierstrass did, and here's the equation that he found. Rho prime of W squared equals 4 times rho of W cubed minus 60 times a certain number G4, which I'll write in a second, rho of W, minus 140 times G6, where Gn means, Gk means the sum Mn not equal 0, 0 of 1 over M plus N tau to the K. So a very explicit equation satisfied by this. And then there's some beautiful theory which goes backwards, which says that if I have an equation y squared equals 4x cubed minus 60 g4x minus 140 g6, if I have an equation like that, there's a way of recovering the basis 1 and tau for the homology. It's a way of recovering the basis for the homology and the tau as an integral of a holomorphic one form over that particular equation. So there's this dictionary between tau on the one hand and this kind of algebraic construction, some solution to some polynomial equation on the other hand. Okay, so I was going to go through a derivation, which I don't have time to do today, but the derivation says if I have a family of complex one tori, this is what these are, with a chosen point, then the family can be put into this form. Y squared, well, I'm going to change the normalization, so I'll change to lowercase letters. Y squared equals x cubed plus f of zx plus g of z, where f of z and g of z depend on the parameter z of the family. So Weierstrass's theory does it for one elliptic curve at a time, and now I'm going to let it depend on on parameters, and if I let it depend on parameters, this derivation is actually an example of an explicit moduli problem. It's not a moduli problem for bundles, but it's a moduli problem in algebraic geometry, similar to what Ugo was discussing in his final lecture. And I'm sorry I ran out of time today. Maybe if I have time later in the lectures, I'll explain how to derive this form. So here I got it in a special case. Here it turns out to be a general property of such families. Well, for certain values of z, f of z and g of z, excuse me, I get singularities in this family of curves. So this is now a one-parameter family of curves, and I get singularities, singular, for special z values. And this general theory, a la Milner, will let me determine determine what the behavior is on the corresponding one cycles when I encircle one of the places where I got a singularity. So what was happening in my simple example was I got this kind of twisting behavior, and I got a particular kind of monodromy transformation. The way I described that monodromy transformation was this one's kind of hopeless. The way I described that monodromy transformation was that a given cycle, say gamma, went to gamma plus the intersection of gamma with another one times delta. And now the intersection properties of cycles on this elliptic curve, right? The elliptic curve has this kind of structure where I've got a cycle this way and a cycle going around the other way. So the two different cycles meet each other. And so what that means in terms of a matrix for the monodromy on the two different cycles is that one of the cycles is fixed and the other one gets an addition from the first cycle. Okay, I don't know if that's visible because of all the background noise, but 1101 is the monodromy matrix which I'm deriving from that previous picture. And that's for the simplest kind of singularity, a quadratic singularity occurring in this process. So what I have to do to make contact with those families is figure out when those families would have a quadratic type singularity. And when they have a quadratic type singularity, I can suppose that I'll be getting a monodromy something like this. Now, there's one wrinkle to the story, which is that in general, I might end up iterating that monodromy. I might go around, I might rotate around that waist n times instead of one time, depending on certain details of the singularity. So I'll have to get to the explanation of that one next time. But the relation between these homology cycles and the tau that I've been describing is that the integral of the holomorphic one form over the two cycles, the ratio of those integrals is the parameter tau that I've been looking at. And this monodromy matrix exactly has the property that it will take tau to tau plus 1, or in this case, it'll take it to tau plus n. So if I can write down families of elliptic curves like that with an f of z and a g of z, and learn when they've got this kind of monodromy or this kind of monodromy, then that would seem to correspond, and this is what the F-theory construction asserts, to exactly what we were looking for, namely solutions of type 2b, which had this SL2z symmetry, which produced this kind of monodromy behavior at certain points as you encircle the loops. So let me just quickly explain how to look at the singularities of this equation with the f of z and g of z. I need to study the discriminant of the cubic equation on the right-hand side. So So I have y squared equals x cubed plus f of z x plus g of z. And I need to know for which z does this have a double root. Well, that's a simple problem in algebra, asking whether a polynomial in one variable has a multiple root. And there's an answer in terms of some polynomial expression in the coefficients. The answer is known, the quantity that I need is known as the discriminant. And in this case, turns out to be 4 times f cubed plus 27 times g squared. So this is equal to 0 if and only if there's a multiple root. Now, I said I wanted to get something that just had a quadratic singularity, so it was like the example, the first example that I did. So I want double and not triple, so we must avoid triple roots. And in 1 second, we'll see how to do that. But anyway, we have a clear condition for getting a multiple root. So this is the first step in the so-called Kodaira-Tate analysis of singular fibers. And let's see. So if z divides delta, then I'm going to get a multiple root as z equals 0. If I want to avoid a triple root, the thing to avoid is having z dividing both f and g. And since z divides delta, if it divides f, then it has to divide g and vice versa. So z dividing delta, z not dividing f, and also z not dividing g, that implies that I get exactly a double root. And now there's an issue of the order of vanishing at z equals 0 of delta. And if that order of vanishing is n, that implies that the monodromy, capital N, that implies that the monodromy is 1, n, 0, 1. So exactly why that order of vanishing corresponds to that monodromy is something we'll have to discuss later, but that's the basic idea. And so this setup should correspond to n d7 branes at that point. Well, the last thing to say about this situation is that there is a beautiful metric that was written down in a paper called Stringy Cosmic Strings, which starts from a family of elliptic curves and produces a metric which in a natural way has the correct deficit angle, 2 pi n over 12, for each of these stacks of n branes out of this data of a Weierstrass equation. And that's the metric which the type 2b string compactified in this situation should use. Okay, so there's more to this story. Obviously, we should think about what happens when there are triple roots. Can we learn something about the monodromy there? There's an interesting and more involved story. And it also starts to involve, when I have a one-parameter family, it starts to involve the type of singularity that I will get in the total space of this equation. That leads me to the codimension 2 singularities, which is the topic of next time. So next time we'll be doing codimension 2 singularities, and by the end of the lecture, we'll get back to this situation and re-examine this set of equations, see where that monodromy came from, and other monodromies like it, which will appear. So I'll stop there and ask for more questions.
Any questions? A few minutes?
Yes.
Is it possible to play the same game but with a different game, the rational conform form and codimension 3 stuff, and then to geometrize the large small volume duality percentage?
So here's the problem. When I'm doing a 7 brane, then I've got the sphere enclosing the singular point in the transverse space is S1, and I can go around that and think about that as a multiple values for a scalar function. If I take, for example, a 6 brane with a 3-dimensional transverse space, then I have a 2-sphere, and it's not that I've got a multiple value of a function is that I have some flux through that two-sphere of the corresponding one form, and I don't have a natural model for that in algebraic geometry to adapt to that situation. So ideally, one would have some way of describing some kind of objects with a variable one form instead of a variable scalar, and then one could do this same sort of construction, but nobody's carried that out. Nobody knows, I guess, the candidate object to use.